I'm going to show you now how we can actually build our circuit in real life using an op-amp. This is called a 411CN. So the reason you need this number is so that you can go online and look up what's called the pinout diagram, because you need to be able to know what each of the individual pins do. For this pinout diagram, we need to supply power. So I've connected negative power to our black cable here, positive power to our red cable here, and then this green one is going to be our ground. And we're actually going to be using earth ground for this because we're using our oscilloscope as well. Our negative power gets connected to pin 4. And we're going to do more things with this in a second, so I'm going to connect this to the blue line here. And we'll connect pin 4 to that blue line so that it is properly connected to our negative voltage. Our positive voltage, which I've connected to the red line up top, is going to be connected to pin 7. We now have power to our op-amp. Our next step is going to be to connect the positive input of our op-amp to ground. So the positive input is our 3-pin, and that is going to be connected to our blue line up top. I'm going to put this over here just to keep it out of the way. Now, I have two 100 ohm resistors, which I'm going to use to connect up the rest of the circuit. We know that our negative input is going to be connected through the resistor to our output. So our output is 6, our negative input is 2. And then that is going to be connected through another resistor to our input. So our input is going to be coming from this blue wire over here, and we can connect that blue wire like so. And then we need to measure our output, which is this line here. We're using relatively small resistors. This is going to cause a problem for our wave generator because it expects to be sending into a very high impedance. So what we're going to do to fix this is use something called a unity gain buffer. So instead of sending this directly into our input there, we're actually going to use a second op-amp. And we're going to hook that up the same way. We need to hook up our negative power to 4, our positive power to 7, and now we've powered the op-amp. So we're going to connect our negative input, which is 2, to our output at 6, and then connect our input to 3. And then we can connect our output to where our input used to be. And so what this does for us is it allows our waveform generator to see essentially an infinite impedance, or very high impedance here, while still supplying the voltage that we want to our circuit to the right. Now, just as a word of caution, the power that I'm supplying these op-amps with is only plus and minus 3 volts. Going higher than that seems to have a negative impact on our output for some reason. So just keeping it to 3 volts and negative 3 volts seems to work really well. Now, the first circuit we want to make is a low-pass filter, and all we need to do to make that is just connect our capacitor in parallel with our output resistor over here. Later, we'll change up our circuit and we will add an inductor in series with our input resistor. And this will create a second order low-pass circuit. And then the final thing we'll be doing is moving this inductor to be in series with this capacitor. And doing that will create our band stop filter. So those are the 3 circuits that we're going to be making. In addition to this unity gain, which you don't need to put in your circuits. I'm doing this just because of how the waveform generator operates. So next, we'll go ahead and look at the output from those filters. All right, so now that we have our circuit made, let's go ahead and analyze it a little bit. First off, I'd like to determine where our critical frequency is. So the way we do this is we simply look at our ratio of in to out, and whenever our out becomes about 0.71 of our input, then we know that that's our critical frequency. So that point for our circuit appears to be right around 1.9 kilohertz. And just as with the passive filter, if we increase past that, it will continue to drop to the point where noise starts to overwhelm. And then weird things start happening again at very high frequencies. So at very high frequencies, our op amp isn't actually able to keep up with the signals that we're sending it. And so it starts to do very strange things. So as long as we stay below, looks like around 83 kilohertz for this model, we should be fine. And then at very low frequencies, of course, we expect to see our output amplitude start to approach our input amplitude. So everything is performing as expected for our simple low-pass circuit. Now I want to show you what happens whenever we plug in our inductor. So as it stands right now, we just have our capacitor in parallel with our output resistor. And remember that we got that value of 0.71 outputs at around 1.9 kilohertz. So let's take a look at what happens when we put our inductor in series. So straight away you see that our output amplitude drops by quite a bit. Now I want to see what just the inductor and resistors are going to do. So I'm going to take out that capacitor. And we can see right away that our output is less than the 0.7. So we can change our frequency by just a little bit. And it looks like our 0.71 amplitude happens around the 1.4 kilohertz range. So if we have both at once, then we would expect that below the 1.4, we should act basically like a low-pass filter. Then as we continue to increase past the 1.8 range, we'll start dropping very, very quickly. So one more thing to look at, note our output voltage at this frequency of 6 kilohertz. Right now it's sitting around 0.1 volts. Now, if we take out one of those, that shoots up to about 0.25 volts. Or if we switch out the other, we end up this time about 0.4 volts. And so if you take that 0.4 that we have from this one, multiply that by the 0.25 from the other, then we end up with that 0.1 value. So really, we're just kind of taking each of these filters and multiplying them together, but we're able to do that with a single op amp. The last circuit we're going to look at is that band stop circuit. And as you expect, as we increase the frequency, it decreases to a certain point and then starts to increase again. Ideally, if we had perfect components here, our outputs at our resonant frequency would end up being essentially zero. But of course, we're dealing with some imperfect circuits, and so our output does not go all the way down. We end up with a minimum value of about 0.3 millivolts. But regardless, the circuit is doing what we expect it to do, which is always good to see.